So section 3 of chapter 12 is changes of state or phase changes. So the definition of a change of state is changing from one state or phase of matter to another. So as I said, you can either say changes of state or phase changes. They mean the same thing. You have definitely seen phase changes before in a diagram format, and you've definitely learned these in elementary school. We're going to go a little bit deeper into the definitions. So I would suggest making sure when you draw this in your notes, you color code it. The exothermic changes are highlighted in green, and the endothermic changes are highlighted in blue. So we'll get to exo and endothermic in a minute. Melting. Melting is a solid changing to a liquid by the addition of heat. And the opposite, freezing, is a liquid changing to a solid by the removal of heat. Evaporation is the change from a liquid to a gas at the surface of a liquid. That's important. And condensation is the process by which a gas changes to a liquid. So I'm sure you know what evaporation is. Anything evaporating outside on the stovetop. Condensation is when you have little droplets forming on the outside of something because it's condensed. And when you condense, you move the molecules closer together and they change from a gaseous phase to the liquid phase. And these are the two that are not as commonly known. Sublimation is when a solid changes directly to a gas. There's no liquid or melting occurring. So sublimation example, the best I can give you is dry ice. So you have a solid piece of dry ice and it immediately changes to a gas. That's why it's called dry ice. There's no liquid forming. And then the least common that people know is called deposition. Deposition is the change from a gas directly to a solid. So condensation is commonly known. You get this outside of the pop bottles or your water bottle. Anything cold kind of pulls in that moisture and condenses it. But deposition is the change from a gas directly to a solid. So this is most commonly seen in the winter when you have moist air outside after a snowfall or even a rainfall, and the temperatures drop so fast that you don't have a liquid forming. Instead, it just is frost. It goes directly to a solid. So getting back to exothermic and endothermic. Exo means outside. So this is when heat or energy is given off by the system. Okay, so you can see the arrows are coming off of my liquid to the outside. Because heat energy is being given off, it feels warm to you. Endothermic is the opposite. Endo means inside. And in this case, the energy, the heat energy, is being absorbed by the system. So it's coming from the outside environment into the system. So you can see the arrows going in. If you're holding this beaker and it's an endothermic process, it is basically taking the heat from your hand and pulling it into the system. So these are going to feel cold. So real quick, just going back to this diagram. Okay, we said exothermic is when heat is being given off by the system. So think about this. It makes sense. A gas to a gas to a solid, deposition. Gaseous particles are very spread apart. Solid particles are very tight. You have to give off heat energy to have the particles stop moving as fast, to slow down, to get into that solid state. Okay, same thing with condensation. Condensation, gaseous particles are far apart, going to liquid where they're closer together. You had to give off heat to get those particles to slow down and condense. And then once again, liquid to a solid, liquid molecules are spread apart, solid are touching, you give off heat to bring them closer together. In all the other ones, the middle part, these are all endothermic, meaning the system is taking in the heat energy. So it once again makes sense. Solid is very tightly packed. A gas is very spread apart. You have to take in heat or energy to get those particles to spread apart. Okay, a solid to a liquid, same thing. The particles spread apart because they're taking in heat, moving the particles apart, causing them to move faster to change state. And then a liquid to a gas, same thing. So usually people get confused on which is which. You have to know what endothermic and exothermic are. And I highly suggest referring back to these two symbol drawings, exothermic going to the outside, endothermic pulling in, and then think about the particles' appearance. Are they spread apart or close together? And what's going to what? So we also have to talk about equilibrium and changes of phase. So a phase is just a part of a system with a uniform composition and uniform properties. So our common phases are solids, liquids, and gases, where they have a uniform phase, and then also plasma. But during the change of phase, you start to have an in-between state happening. So equilibrium, if you're in equilibrium, basically you have something happening at equal rates, okay? So something is happening in which two opposing changes are occurring at the same rate in a closed system. So theoretically, matter should not be able to get in or out of a closed system, but energy like heat energy could. This is definitely theoretical. Obviously, capping something, we consider it a closed system, but unless it's vacuum sealed, it's very hard to say that nothing's getting in or out, even if you can't see or feel something getting in or out. So an open system would be like this, where you have a pot of water being heated, and not only is heat energy coming off of this, but matter is also coming off of it. There's no lid, so the water is going to be evaporating, changing to a gas, and that gas will just escape into the atmosphere. A closed system, like I said, theoretically, there is no matter getting out. So all of the evaporating water is going to be stuck in here as vapor, or it may condense on the lid. But energy, the heat energy, is still going to be able to get out, which is why the pan feels hot to you. So Le Chatelier's principle basically says a system at equilibrium will remain so unless it's disturbed by stress. And the system will respond to this stress by forming a new equilibrium point. So it's kind of like humans. If you're very mellowed out and having a good day and something disturbs you, you may be disturbed by that stress, but hopefully you're going to respond in such a way that you're going to push that stress aside, try to ignore it, and form a new equilibrium point where you can once again be mellowed out and stress-free. So a stress in this format can either be a change in temperature, pressure, or volume within the container, or the concentration of the substance. I'm going to skip over this. We don't talk about Le Chatelier's principle that much anymore, so I'm going to skip over the examples. Just know what his principle says. So the equilibrium vapor pressure of liquids, or EVP. The equilibrium vapor pressure of a liquid says a vapor that is at equilibrium with its liquid exerts the same force or pressure as the liquid. So the vapor and the liquid are exerting the same force or pressure. This is definitely temperature dependent. If you increase temperature, you increase the EVP. Be aware that boiling is different from evaporation. Evaporation, we said that is where you have a change happening directly at the surface of the liquid. Boiling is when you have a change within the liquid to a vapor. That's why you have bubbles down inside as well as at the surface. The surface is where it starts to actually evaporate, but it begins within the liquid itself. So boiling and evaporation are not the same thing. And this boiling point can occur when the equilibrium vapor pressure is equal to the atmospheric pressure. So that's why sometimes it takes a while for something to start boiling because it's temperature dependent and it has to equalize with the atmospheric pressure. So looking at this diagram here, evaporation, it says bubbles cannot form in the liquid since vapor pressure is less than atmospheric pressure. But with boiling, you're increasing temperature, vapor pressure can overcome the atmospheric pressure and escape into the gaseous phase. So it's not just happening at the surface, it's actually happening within. And that's why boiling causes evaporation to happen a lot more readily. If you leave a pot of water sitting on the stove for 2 days, that water's still going to be there. The level just may have went down a little bit. If you leave something boiling on the stove for more than a little bit of time, the water will be completely gone. So once again, if you increase the temperature, you increase the vapor point, the equilibrium vapor pressure, and eventually that boiling point is reached where you can overcome the atmospheric pressure. So boiling point is defined at the temperature at which the equilibrium vapor pressure of a liquid is equal to the atmospheric pressure. That is boiling point. So just be aware, boiling point at sea level is standard, boils at 100 degrees Celsius or 212 degrees Fahrenheit. But depending on where you're at atmospherically, that may be lower or higher. So you can see that at sea level, our normal boiling point is 212 Fahrenheit. But if you increase altitude, the boiling point actually lowers because it's easier to reach atmospheric pressure. That is why sometimes if you read directions on a cake box or something, it will say at high altitudes, cook it for less time or cook it at this specific temperature. So when water is boiling, when that boiling point is reached, the temperature is constant even though heat is being added. So once you start something boiling, increasing the heat's not going to do anything. As I said, at high altitudes, the pressure is going to be lower because of how high up you are in the atmosphere. So liquids actually boil at a lower temperature, and sometimes foods need to be cooked for longer because there's a lower temperature. So this is a box of, I believe it was cake mix. It says high altitude over 3,500 feet. Preheat oven to 350. It's actually telling you to add flour, and then it's telling you to bake it at 350, but for a longer time than the normal directions. Okay, molar heat of vaporization is the amount of heat required to evaporate, hence vaporize, evaporate 1 mole of liquid at its boiling point. Moving on to melting and freezing, the freezing point is the temperature at which a solid and a liquid are in equilibrium at 1 atm. So water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. So talking about the molar heat of crystallization, the amount of heat released as a liquid freezes or crystallizes. So we said that that is giving off heat to make the particles closer together. So how much heat is released to cause it to freeze? And then the molar heat of fusion is the opposite. It's the amount of heat energy required to melt. So you're taking in heat to move the particles farther apart to cause them to melt or to become a liquid. So a lot of definitions there. The stronger the attraction between the liquid particles, the more energy that's going to be required. So just understand that it's dependent on the substance itself. So a lot of definitions there. Just make sure you read over those and understand them. And we're going to get into the last part of our section, which is phase diagrams. So a phase diagram is just basically a pressure versus volume graph that shows the conditions under which the phases of a certain substance exist. So you may see something that looks like this, very plain, but giving you a lot of information, or you may say something color-coded with more detail on it. Either way, you can get the same information. So this phase diagram specifically shows you how the states or the phases of a system for whichever substance can change with temperature and pressure changing. So every substance has its own phase diagram. Sometimes they're labeled, sometimes they're not. Okay, so looking at this phase diagram, there's many things you can see here. The portion that's most to the left is always going to be your solid. Liquid is always in the middle, and then gas is always maybe towards the bottom and towards the right side. And these may change in size depending on the substance. So pressure in atmospheres and temperature in Celsius. And you can kind of learn, at which temperature is it going to change from a liquid to a gas? At what temperature will it change from a liquid to a solid, and so forth. So triple point. A triple point indicates where the temperature and pressure coexist as a solid, liquid, and gas. So the temperature and pressure at which this substance coexists as a solid, liquid, and gas. It's where all the lines intersect. Okay? Now, theoretically, this is great, but we know in real life, you can't have something that's actually coexisting in all three states of matter. But theoretically, that's what the triple point is. Triple because you have 3 states of matter. Critical temperature is the highest temperature at which a substance can still exist as a liquid. So it's kind of the cutoff here. Critical pressure is the highest pressure as it can also exist as a liquid. So notice you just kind of draw a dot at the end of your line between liquid and gas, and you can draw a line straight down to determine the critical temperature, and you can draw a line straight across to determine the critical pressure. The critical point is the intersection of the critical temperature and critical pressure. So that's where that dot is. And this is a unique value to every single substance because every phase diagram will be different. Okay, so just looking at some different phase diagram examples. Once again, to the left is always a solid. The liquid is always in the middle. The gas is always to the right side. Temperatures across the bottom. Pressures across the top. The triple point is where the lines intersect. And the critical point is at the top of the line between the liquid and the gas. So once again, here's another example. And you can have one that looks like this with actual numbers to allow you to figure out specific values. So let's actually analyze one. So use this phase diagram to determine these things. So using the A, B, C, D, E, F, G, H, tell me or answer these questions. So pause the video, I'll give you a second. Try to answer these. Okay, so where is the substance a solid at? That would be A. So let me get my pen here. I'm going to use purple. So all of this region, the whole way up here, is going to be a solid. Where does the substance exist as a liquid? That's going to be G. Okay, liquid's always in the middle. So all of this region, and I always color code mine. So if you have color pencils or highlighters, I'm not saying go crazy with coloring, but if you can just generally outline it, I think it's helpful. Okay, and then where does the substance exist as a gas? That would be H. So that's always the same. The size may not be the same, but the general locations are always going to be the same. Okay, where is our triple point at? Triple point is where all of these intersect. So that's going to be B, right here, the intersection of all the lines. So 1 line, 2 lines, 3 lines. Sometimes it doesn't look like 3 lines, but where does the intersection occur? Triple point is when there's a coexistence of a solid, liquid, and gas phase. The critical point is going to be D. It's the very top of the line between liquid and gas. That's the highest temperature and the highest pressure a substance can exist as a liquid. Normal freezing point, that's going to be E. Okay? Now, you would have to know what substance this is, but consider a liquid to a solid. Freezing point is represented by E. That would usually give you a value. And normal freezing point F. That should say boiling point. Liquid to a gas. Sorry about that. Okay, let's try. Whoops. Let me clear that. Let's try another one. Oops, I guess that was it. So let me go to this one real quick. You're going to have many phase diagrams to look at. So just be aware that, for this example, here's our triple point. Here's our critical point. You have solid, liquid, and gas. I could specifically ask you, what's the temperature at the triple point? You just draw a line straight down, and I have to give you values. Okay, so it's kind of a guesstimation, but if you don't have a ruler, just use a piece of paper, put it up to your screen, straight down. If I ask you the pressure, you just draw it straight across. Where does it intersect? Same thing with the critical point. Straight down for temperature, straight across for pressure. Okay, so you're definitely going to have examples of this. This chapter is a lot of vocabulary and terms, and then being able to analyze and interpret phase diagrams. So in class, I would be able to help you a little bit more with more examples when you come to them. So please be aware that if you need help, chat me or Zoom with me on Wednesdays, and I will help you out.